Let's start considering now propagation in a real environment. When we have a transmitting antenna and a receiving antenna, we'll encounter all sorts of elements that actually will modify or will deviate our propagation from what we would call free space conditions. We will have reflection in obstacles, we will have scattering, we will have diffraction because there will be obstacles that will be obstructing our line of sight. We will have atmospheric effects, for instance, we'll have refraction, we'll talk later on about that, or we also have attenuation due to atmosphere. So actually, compared to free space propagation, in which we have what we call line of sight and no multipath, this environment is much more complex and there are many more elements that have to be taken into account. Now, when we consider free space propagation, we have a transmitting antenna and a receiving antenna. They are spaced a certain distance, and in that case, we can very easily compute the received power. We know that the incident power density on the receiving antenna is the transmitted power, the gain of the transmitted antenna, over 4 pi d square. Now, this antenna has a certain effective area, so the received power is the incident power density times the receiving antenna effective area, and we know that we can express the effective area of the receiving antenna as a function of that antenna gain. So when we substitute, we obtain something like this, that when we rearrange the terms, we obtain this. Here we have the transmitted power, the gain of the transmitting antenna, and the gain of the receiving antenna. Of course, those parameters depend on what sort of antennas we are using, the power we're using, and so on. But we have this term that depends on lambda, the wavelength, that is the frequency, and the distance. That term is what is usually called free space path loss, and this is its value, lambda over 4 pi d square, that we can express in dBs, well, as 20 times log of 4 pi d over lambda. So that's the way free space propagation path losses look like. Here we are plotting the loss in dB, in a dB scale, and this is a log scale of the distance, not the absolute distance, but the distance in terms of the wavelength. So for instance, at 10 wavelengths, we have an attenuation, or we have a free space loss of over 40 dBs. So now let's think a little bit about the meaning of that. For instance, consider a system operating at 2.45 GHz. That could be a Bluetooth or a Wi-Fi system, something like this. At 2.45 GHz, the wavelength is about 12 centimeters. So 10 wavelengths is about 1.20 meters, maybe 1.5 meters. So that means that in that link of 1.5 meters, we already have free space propagation losses of over 40 dBs. Notice that this is a huge attenuation, probably an attenuation much larger than we can have using any cable system or wire system. If we have these frequencies, if we have a cable of 1.5 meters, the attenuation would be much smaller. So free space propagation losses, actually, we pay a very heavy toll for short distances. On the other hand, that slope has a slope of what we call 20 dBs per decade, or 6 dBs per octave. Now, 20 dBs per decade means that every time we multiply the distance per 10 times 10, our attenuation, or our losses, increases in 20 dBs. Or that 6 dBs octave, what it means is that every time we double the distance, we have an additional 6 dB losses. So that means that if you already have a link that is operating well, and it has a distance of 10 kilometers, and we increase that distance from 10 kilometers to 20 kilometers, then we only have 6 additional losses due to free space propagation. So that's the first thing we have to take into account, is that free space propagation actually operates in a different way that operates in guided systems, in which attenuation is proportional to the distance. Now, let's see an example of real measurements of propagation. This is an experiment in which we have taken an airplane. Now, this may seem like a large airplane, but this is actually a very small radio control airplane that has maybe 1.5 meters wingspan. But we have placed two transmitting antennas in that airplane, and then we have two receiving antennas here on the ground. This model airplane, we have a GPS, so actually we can track its position, so we can compute the distance between the airplane and the receiving antennas. So when we plot the received signal, we obtain something like this. Now, that green line is what we would explain, it's actually free space propagation losses. And those red and blue curves are the actual received signal, well, that depending on the combination of transmitting and receiving antennas we were using. So actually we can see that, well, free space propagation losses explain part of the picture, but reality is much more complex. And notice that this is not a particular complex propagation environment, but actually you can see how the received signal has very strong variations around that expected value given by free space propagation for the free space propagation model. Sometimes we receive more signal, sometimes we receive less signal. As a matter of fact, if we look, for instance, in a time scale, the received signal, we can see that even for very short, in a short time scale, we can see strong variations. Notice that these are seconds, so in less than 1 second, we can see strong variations of the signal, maybe going up and down a few dBs, and of course, well, that model airplane is not moving too fast, okay? So actually, with this experiment, what I just wanted to show you is that in real propagation environments, actually what we're obtaining is something much more complex that is not fully described by the free space propagation model. So let's see what sort of phenomena we can see. Now, of course, when we talk about wave propagation, electromagnetic waves are not the only sort of waves we can find. So for instance, we have been talking already about scattering. And maybe here you can see a nice picture of what scattering is. Here we have a wave incident to this rough surface, which is the rough surface of this shore, and you can see that we don't have a clear reflection, but we have multiple waves coming out from that reflecting surface. But also we can see how these scattered waves interfere with those incident waves, and we can see those multiple ripples, maximum, minimum, going up and down due to the interference. Other sort of phenomena that we will be talking about is, for instance, diffraction. Here we can see how, well, we have this corner here, we have the incident waves, but we can see that how suddenly here there is a wave appearing, which is sort of a diffracted wave, a wave that will be propagating, okay? And probably, well, we'll be able to see that wave when it propagates. Probably we'll see that wave here, that scattered wave here, while we would expect that actually that area here will be shadowed and we shouldn't see any wave. Okay, so this is the case of diffraction. So this is a very simple view-on image, not exactly, they are not electromagnetic waves, but when we consider our propagation models, we will have to consider all these different effects: scattering, diffraction, reflection, and so on.